Okay, good morning. Okay. Thanks for coming to our second astrobiology school at Observatório Nacional. It's a great pleasure to have you all here. This is the second edition of this school. It's a biannual event of the Observatório Nacional. The first edition was in 2014. Now we have the second edition, and hopefully we have the third edition in 2018. Okay. So I would like to say a very special thanks to our speakers, Dr. Freddie Adams and also Dr. James Jenkins for coming, and also the other speakers, Dr. Enio Silveira and also Isa Oliveira. Thanks for coming, for accepting our invitation and for coming. And I would like also to say thanks to our director, Professor João dos Anjos, and also the head of our department, Dr. Jailson Alcanis, for all support and also the effort to help us. Okay? And I would like also to say thanks to the organizing committee, okay, composed by me, by Dr. Vinicius Bordalo, Dr. Renato Duque, and also Dr. Isa Oliveira. Thanks for the hard work to make this school possible. Okay? So before we start, I would like to invite our director, Professor João dos Anjos, to say some words. Thanks.
Well, I'd just like to welcome all of you. It is the professors that are coming for the courses, to give the courses, and also the students. It was a very big effort due to the difficulties that we had this year in Brazil, that it was difficult to get the visas, for instance, for Professor Fred Adams, that I think was Friday, you could get the passport.
Well, I got a Thursday. So.
Thursday. But anyway, the important is that we managed to get all the speakers here, the two speakers here. And then I'd like to thank not only Professor Fred Adams, but also James Jenkins, thank you for coming. And also the Brazilian speakers, Enio and Isa and all the others. And I invite you, this week we are celebrating the National Science Week in Brazil. And then we have a lot of activities at the Observatório Nacional during all the week. And you are also invited to get around for the observatory and to see there will be other institutes also that are coming here, CBPF, INPA, all the institutes of the Minister of Science and Technology. And also you have some observation at night. The Luneta 46 is now working. That is, we will re-inaugurate it. And then I invite you to look to the moon and Saturn and this kind of thing. Well, many thanks to all of you, and welcome to the city and the observatory. Thank you. I don't know if I say thanks to the organizers, but I think so, no? Vinicius, Isa, Renato, and Marcel. Thank you all for organizing.
So good morning. I guess, all right, I'll use this. So the funny thing with the visa is that he actually got a 10-year visa, and his passport expires next year. So anyway, it's a fantastic pleasure to introduce you to Fred Adams. He finished his PhD in '88 with Frank Shu at the UC Berkeley. From there, he did a tour at the CFA, and then went to the University of Michigan, where he's a full professor there. He is one of these very eclectic and efficient scientists that has an incredible variation of interest and has done fundamental work in very different areas. And what I mean different is really different. It varies from extrasolar planets, star formation, IMFs, young stellar objects, all the way to inflationary cosmology. And so it's right, telling what he's done. As he said, he would take probably a full lecture, and I do that. But one thing that I found is very interesting. He has 2 books published. One of them I actually checked a little bit the translation from Portuguese to English, I guess, right?
No, the other way around. English to
But
Portuguese.
the book was Polish. This book is pretty popular. It's called The 5 Phases of the Universe, or you can correct me if I'm misciting. And he published this right after he got a review of modern physics, The Dying Universe. So there's the 5 phases, and now there's a new book called The Essence of the Origin of Existence. So even though it may look like he's going backwards in time, like first about death and then existence, I think it's more of an optimistic way of thinking, from death to, and very recently has been working on a very interesting paper. He's going to talk on the last lecture here, which is going against the idea that the universe has to be very fine-tuned for life to exist. According to his studies, it doesn't need to be that fine-tuned. So, not to waste some more time, I'm going to leave you with Fred.
Okay, well, thank you very much for the kind introduction. Thank you for inviting me to be here. It's very good to be in Brazil. Thank you for all of your effort in getting me a visa. It was no small task, but it was very much appreciated. So, what I'm going to talk about today, well, I'm going to first outline, I've been commissioned to give a series of 4 lectures on stars and star formation and so on. So my role, at least as I see it here, is that we want to talk about astrobiology and habitability. And I think square one for an astrophysicist is you need stars. And second, you need stars to make solar systems. So what I'm going to do for the first part of this series, the first 2 lectures will be star formation processes. And I'm calling this star formation processes instead of the theory of star formation for a particular reason. You'll see why as we make that play out. So the first 2 lectures are all about star formation. Star formation includes disk formation and a little bit of planet formation, because we have a whole speaker in James who's going to do planets. I'm going to cede the subject area of planets largely to him, so you're in charge there. And then for my 3rd lecture, I'm going to talk about what we can say about the birth of our own solar system, in particular the birth cluster of it, and that raises a number of issues, namely how environmental effects can affect solar system formation, solar system structure, and solar system habitability. So that will be lecture 3. And then for lecture 4, which is conveniently located on Friday, I'm going to go off into Never Never Land and talk about the idea of can stars live in other universes even? Because Renato asked me to do this. It's all his fault. And it's sort of a way to expand our horizons and look at sort of what are really the basic essence of the constraints or the necessities we need for habitability in general, right? So kind of like by stepping back to the big picture, we can kind of understand the little picture we live in a little bit better. So that's why I'm doing it. Plus, it's just kind of cool, right? So we'll see how that goes out. So let's start with lecture 1. Lecture 1 is star formation processes, number 1. Okay, so here in our own galaxy, star formation is this vitally important process. So I like to say we have sort of this karmic cycle of stellar birth and death. Clouds of molecules form, and they form stars. Stars go through pre-main sequence phases. They burn hydrogen in main sequence phases. They go through post-main sequence phases and die. They return some of their material back to the interstellar medium. 3 out of 1,000 blow up in supernovae and enrich the galaxy with elements. Some of the supernovae produce neutron stars. Some produce black holes. Most of the rest of them produce white dwarfs. Some of the mass is locked up in these degenerate remnants, but most of it's actually returned to the galactic supply, and round we go. So the star formation process is one of the most important parts of this, and that's what we want to talk about. Now, the history of this is that, as Renato mentioned, I did my thesis in the 80s, which is now a long time ago. And at the culmination of this time working with Frank Hsu and also a colleague Susanna Lizano, we put together this theory of the 4 stages of star formation. And the general idea is simple, that stars form in molecular clouds. And in the molecular clouds, small subcondensations called molecular cloud cores form. And those are the actual sites of star formation. You can see that in the 80s we didn't have as good of computer graphics as you guys do now. So you graduate students are lucky by comparison. They only gave us this many dots, that's all we got, right? So anyway, these cores will slowly condense. They're controlled by magnetic fields, as you'll see in more detail than you want to very shortly. And they collapse from inside out, and when they collapse from inside out, they form protostellar objects. A protostellar object consists of a stellar-like body in the middle, which is hydrostatically supported, surrounded by a circumstellar disk of material, and then the star disk system is deeply embedded within an infalling envelope of dust and gas. At some point fairly early in the evolution, the star is able to generate a powerful outflow which punches through the infall along the rotational poles of the system. It gradually widens with time and separates the star and disk out from its environment. And then we're left with a isolated or a separated star disk system. Now, we call this star formation processes, or I'm calling these star formation processes for a particular reason. For each step of the way of this basic picture that I just described, we can observe the starting point and the ending point. We can calculate using equations, ones that I'm going to actually show you, how to get from point A to point B. And we can match the theoretical predictions up with what we see. So for each step of this process, we have theory. We don't know everything, and I'll try to make clear what we know and what we don't know, but we have a working theory that describes each phase of this process along with observational confirmation. That is the bottom line of the story I'm trying to sell to you over the next 2 lectures here. Now, if you go to a cosmology talk, they usually begin by, because they're trying to put star formation into cosmological simulations, and no offense to the cosmologists among you, but they start by saying, we don't have a theory of star formation. And then they say, well, that means we're going to write some recipe for if the density gets above this, we'll like make stars out of magic. And then they will make fun of the star formation people for not having a theory. Now, what they're talking about is not altogether wrong. What we have is we have a theory of each process of getting from A to B. And like I said, we're largely successful in understanding that. What we don't have, and this is the only thing that the cosmologists want, and that's why they criticize it, what we don't have is we don't have a single function that says if I start with a cloud with this metallicity and this density, what's the initial mass function coming out the other end? In other words, from a cosmological simulation point of view, and again from a galactic ecology point of view, you actually don't care about anything I'm about to tell you, in that you don't really care about how the physics works and how the nuts and bolts of the processes work. You want to go to the back of the book and see what the answer is. What is the initial mass function as a function of metallicity? And where we are now with star formation theory is that we can understand each one of these separate processes in probably more detail than you want. But that won't stop me from telling you about them. But we don't have a single comprehensive theory you can just push the button and get the IMF, the initial mass function, out the other end. We would love to have that, and we're working towards it, but the process is very messy, as you're about to see. Okay? So that's kind of the big picture. The outline of what I'm actually going to talk about is here. I'm going to start by talking about the core formation problem. Remember, those little dots represent molecular cloud cores, and I talk about how magnetic fields will control that process. Now, in the literature, if you're not reading it very closely, you'll see that there's apparently 2 different theories of how cores form. One is that they're formed controlled by magnetic fields, and one is that they're formed by turbulent fluctuations. Both are true and both are wrong. The story is that molecular cloud cores are formed by magnetic field diffusion, which are influenced by turbulent fluctuations. In other words, both sides are right. Since some people work on one and not the other, you can get the impression that it's an either-or thing. It happens to be a both thing, and I will spend a lot of today's lecture justifying that. Then I'll talk about the collapse flows, the role of ionization, the rotation of the collapsed flows, which gives us disks, and then a little bit about spectral energy distributions and disk physics, but that will be largely in tomorrow's lecture. Okay? So let's start from the very beginning. When you read a textbook from the 50s, what you see is that there's like two main problems of star formation. And the people in the 50s were not wrong, okay? So this is a good place to start. The first problem is the angular momentum problem. We know what angular momentum is. I understand there's some biologists in the room, so I'll try to motivate this. Specific angular momentum is the amount of rotational motion that you have. You can measure the specific angular momentum by a velocity times a length scale. And here's the problem. If you look at the scale of a molecular cloud core, these are these big million solar mass nurseries of stars that we see. So they're much larger than a star. They have a specific angular momentum in CGS units of 10 to the 24. That's 10 to the 24 centimeters per second times centimeters. Okay, don't worry about the units, it's only the relative size that matters. If you look at the molecular cloud cores, the things that are actually forming the stars, the specific angular momentum is smaller by a few orders of magnitude. It's only 3 times 10 to the 21. But here's the problem. If you actually look at a star, and you say, I'm going to rotate it so fast that it breaks up, which is the fastest you can possibly rotate it, it has a specific angular momentum of only 3 times 10 to the 18. Now, those of you who can do math realize that 3 times 10 to the 18 is almost 1,000,000 times smaller than 10 to the 24. So in order to form a star, you have to get rid of all of the angular momentum. You only have 1 part in 1,000,000 left. That's the classic angular momentum problem. How is it that on the scale of a cloud, which is the star-forming nursery, you have so much angular momentum, but on the tiny scale of the star that you're forming, the product you're making, the angular momentum is so small? Well, clearly, you have to transfer angular momentum. You have to move it around because, as you know, angular momentum is still a good conservation law. Angular momentum has to be conserved. So the way in which this process happens is vital to forming stars. Now, I'm going to pose this problem. I'll go through the star formation paradigm, and then I'll come back to this, how this problem is resolved by our current understanding of these processes in about 7 hours at the end of the lecture. I get 7, right? I'm just seeing if you guys are still awake. The other classical problem is what's called the magnetic flux problem, rather. So here's the deal. Magnetic fields don't seem that weak, or don't seem that strong, rather. They seem weak. We only have about 3 to 10 microgauss out in the middle of the galaxy. But if you take the flux ratio divided by G, there's a critical mass you need to make a magnetic field or a cloud collapse in the presence of a magnetic field. So if you look at the scale of clouds and cloud cores, the radius is a couple of parsecs, or the size scale is a couple of parsecs, and the field gets compressed from 10 microgauss up to maybe 30 microgauss on the scale of the cloud. You see that you need 1,000 solar masses to compress the field. And this is a problem because we don't have any stars of 1,000 solar masses. What this says at face value is that in order for gravity to beat the magnetic field, as in win against it, you need 1,000 solar masses of material. But we want to make stars, and the typical star is actually not 1 solar mass, it's like 1/4 of a solar mass. So there's this factor of 4,000 that we have to get rid of, or we have to deal with. We cannot make objects as small as stars in the face of magnetic field support, even though apparently magnetic fields are rather weak. So magnetic flux must also be lost in order for stars to form. But here's the problem. It's called there are no monopoles except for at Stanford problem. You guys are too young to get the joke. In February 14th of 1982, a monopole was discovered at Stanford University, which of course was really just a heavy nucleus because there are no monopoles in the universe at that time. That was the only one we had, right? So, except for that one, there's no monopoles in the universe. And what that means is that magnetic field lines cannot end. And what that means is you can't get rid of flux. So what that means is that when flux is lost, it's actually not lost, but rather it has to be transferred out in the same way our not quite the same way, but in a similar manner to the angular momentum has to be lost. So we have two big problems right from the beginning in forming a star. One, there's too much angular momentum, and two, there's too much magnetic field. So we got to get rid of them, okay? We got to get rid of both. So what I'm going to talk about is the actual detailed process by which we get rid of magnetic flux, and that's called the core formation problem. So now I'm going to get into some of the detail. So we want to make a core. So we have a big cloud, which is 1 million solar masses, and on the scale of a core, the mass scale, as we'll see, is many solar masses, 7, 10, something in that ballpark. And remember, we're making stars that are a quarter of a solar mass or a half a solar mass. So the core scale is much bigger by about a factor of 10 than the stars it's making, but it's much smaller than the cloud that it lives in, which is 1 million solar masses, or maybe 10 to the 5, okay? So what we want to do is we want to study how cores form and evolve through magnetic field diffusion, which is called ambipolar diffusion because we have to give it a confusing name. There's a whole host of work on this, but I'm going to try to boil this down for you. So the simplest way to understand magnetic field diffusion, which is the basic process by which cores form, and hence the basic process by which stars form, we have to do the following. So even though everything really happens in 3 dimensions, I'm going to give you a 1-dimensional problem. So here we have a plane parallel geometry where the midplane is here. The z direction is up and down. Gravity acts towards the midplane, and magnetic fields support the layer from collapsing. Now here's the key essence of magnetic field support. You can ask yourself the following question. How does a magnetic field actually support a cloud? Because the cloud is largely neutral. Think about that for a moment. The cloud is largely neutral. The ionization rate is only 1 part in a million-ish. But the magnetic field does not couple to neutral gas. So why do we care about the magnetic fields at all? It's a good question. Well, the answer is that the magnetic fields are coupled very tightly to the 1 part in a billion particles that are charged. So they're tightly coupled. In order for the magnetic field to exert a force on the neutral component, it has to do so through a friction. There has to be motion between the neutral component and the charged component, or the ionic component, in order for a force to be felt. So that leads to the interesting concept that magnetic field support must be synonymous with loss of magnetic field support. Because in order for the cloud to hold up the neutral, or the magnetic field to hold up the neutral cloud, there has to be motion of the neutrals with respect to the ions so they can feel the force. But the ions are tied to the field, so the field is actually slipping by the neutrals as this process unfolds, and that's ambipolar diffusion. This, in this box, is the key term. It's the friction term exerted on the neutrals by the ions that you see is proportional to an ionization, or a cross-section, which depends on ionization, and the density of the neutrals and the density of the ions, and the relative velocity between them. Now, I'm going to show you equations. I don't want you to get too worried about the equations, even though I'm going to show you a lot of them. We're not going to go through the algebra of these, okay? I'm going to use these as a reference point. These slides will eventually be posted somewhere. Marcello's going to put them up somewhere, right? And you can go through them at your leisure if you want, or you can pretend, or they don't exist and not go through them as you want. But I'm going to show you the equations anyway, just so that you'll know what I'm talking about and use them as a reference. So what I'm going to derive for you later is that the field works through a diffusion equation. And this is the diffusion equation. We have d by dt of magnetic field over density. So it's a d by dt is equal to a d by dx of something, d by dx. X is actually the surface density in this case, and d is the diffusion constant. The diffusion constant actually depends on the magnetic field itself, as well as the ionization and the density and the frictional term that we just went through. Okay? So the history of this is that in the 80s, it was put forth that magnetic fields were the only controlling factor in making cores. And that list of people I showed you solved this diffusion equation that I just showed you in more and more and more detail. And it more or less works. But the problem is that once we got good enough statistics on how many molecular cloud cores there are and how long they live, the simplest version of the theory actually takes too long. The cores form too slowly. The magnetic fields are actually too effective at supporting the cores. The second thing we found was that if you use the simplest form of the theory, the diffusion is so slow that at any given stage, the actual infall velocity is essentially zero. But what we found is that when we actually look at the cores in detail, and we're finally able to do this in the 90s and the early 2000s, the cores are actually not, even before the cores eventually collapse, and when they collapse we can see the free fall velocities, but before they collapse they're not static. They're not collapsing, but nor are they static. They're condensing at about half the sound speed. To be collapsing, you have to be supersonic, okay? So you can be condensing but not collapsing. It's almost like being less than more than the sound barrier, but not quite that simple. But what we see is that the condensing cores, before they collapse, are slowly moving in at half the sound speed. And it's half the sound speed, not the sound speed, not zero, and we can measure it, but they're not collapsing. And then we also found that the observed cores resemble what are called Bonner-Ebert spheres with a constant density center. If you take the original version of the theory to its logical extreme, you produce a very, very centrally condensed power law distribution of density. But when we look at cores, and the cores that we can see the best are the youngest, we see a constant density center. And then we also see that the cores are not static themselves, but they're moving through the clusters that they live in, but they're moving through slowly, and again, about half the sound speed. So for all four of these reasons, the original version of the ambipolar diffusion picture is one step inaccurate, because instead of having this smooth, quasi-static, very slow formation process, everything has to be more dynamic. So this is a picture of what I mean by a Bonner-Ebert sphere. You see it has this long, this is the density distribution, actually surface density distribution versus radius. There's a big central region that has constant density. It doesn't just keep going up, okay? So what I'm going to show you now is that if you do the calculation a little bit more carefully, and you put in more, well, if you do two things. If you remove the quasi-static approximation, and you put in turbulence, and I do those in subsequent, in pieces, then you can actually solve all four of the picture, or the dilemmas that I showed on the previous slide. So we're going to take another look at this picture. Now I'm going to go through this calculation for the picture, for purpose of the lecture, kind of quickly, because I'm going to just leave the equations on the slides for you guys to look at later. But I'm going to try to outline the physics of it and a little bit of the calculational technique that we use. So if you have density contours in a magnetic field, you get these more or less straight lines that are kind of bowed are the magnetic fields, and these sort of figure 8-like pictures or contours are the density contours. This is just what they look like, and I'm showing you. But what you can see is that as you crank up the field strength relative to the mass, the structure gets more and more flat, more and more disk-like. So there's actually a very cool calculational technique that one can invoke. We want to do the calculation for a big, extended, fluffy, almost round structure. The structures we see in the sky are kind of not round or flat at the 2-to-1 aspect ratio, so they're not very flat. They're just a little bit flat. But yet, we don't want to work that hard. So what one can do is one can take the sort of two-dimensional structure, flatten it to a disk structure, do the calculation, and then fluff it back out. And that actually works really well, surprisingly. And that's what we're going to do. And I'll tell you why we're doing this. So here's the equations that one has to solve. Now they look like sort of a big mess, but it's actually not so bad. This is just the continuity equation, so it tells you physically mass is conserved. This is just the force equation. This tells you F equals ma. This is pressure force, gravitational force, magnetic field force. We have to say what the gravity and magnetic field force are, and they're written in terms of the surface density and the field strength. And then this kernel function and the integral function are what you have to do to solve Poisson's equation, which we're not going to worry about, but you have to do it. Okay? And then when you do one more equation to close the field, which is the time evolution of the magnetic field, which is basically Maxwell's equations combined with the fluid, which you could write in the form of a diffusion equation, which is shown here. So this is just a diffusion equation for the field. Okay?
One question.
Sure.
These theories are in the 80s. They did not consider, for instance, the dark matter, the gravity from dark matter. This has any influence to this in the star formation, or just in galaxy formation?
That's a very good question. And the answer is that on the small scales that we're dealing with here, the dark matter doesn't have a big enough contribution. And I can tell you why. Okay. So for those of you who, well, don't know, the dark matter is very important on large scales. It has a density, it has a total mass density, which is 6 times the baryonic component, right? So the simplest way to think about it is that the density of protons in the galaxy is 1 particle per cubic centimeter. It's always easy to remember 1, you just have to remember the units, right? Now, because the dark matter particles are probably heavier than protons, they're 10 or 20 or 50 times the mass of the proton. Since we haven't discovered them yet directly, we don't know what their mass is. But in order of magnitude, if they're 10 times heavier, but they have 10 times more mass density, their number density is also about the same, about 1 particle per cubic centimeter. Okay? You know, order of magnitude, that's correct. Now, the molecular cloud cores that we're talking about, they have a typical number density of 10,000 particles per cubic centimeter. So the density of, if the dark matter doesn't collapse, it's just this background field. So the dark matter has a density which is about 10 to the 4 times less than the baryons we're considering. So it's sort of a 1 part in 10 to the 4 correction. But it's actually even less than that because the dark matter does not, on these scales, have any structure. So it's like embedding your problem in a constant density background. So the forces exerted on on the actual cloud by a constant density background are even less than 1 part in 10 to the 4. So if we actually knew what we were doing at the 1 part in a million level, then we would need to include the dark matter perhaps. But I don't think we're quite there yet. I'm kind of worried about 10% effects here. And that's important because it's important for you guys to come away with this knowing just how well we know what we're talking about, right? What do we know, what we don't know, right? And I would say we kind of know what we're doing at the 10% level. We do not know what we're doing at the 1 part in a million level. Okay, so how are we doing on time? So the way in which we address this question is we use something called similarity or self-similarity. So just for purposes of educating the students, let me tell you what self-similarity is. So if you have a problem, in this case, we're trying to solve for the time evolution of the fluid fields, namely the density profile, okay, and the velocity profile that goes with it, and also the magnetic field profile that goes with that. Okay, so we have basically a density profile rho of r. That's our solution, that's what we're trying to solve for here. If you have a problem where the solution at one time is a stretched version of the solution at a previous time or a later time, then you can scale one solution to another, okay? And this self-similarity arises in a whole class of physical problems. In particular, it arises in the formation of a core, which is what we're doing now, and it also arises in the collapse of that core after it's formed, which is what we're going to do next. And basically what this means, and the reason why we do it, is that it involves scaling out the time dependence of the solutions, and then we can turn the partial differential equations, which, as you saw in a couple slides ago were just a mess, into ordinary differential equations. And that comes to my first theorem that I want you to come away with, is that ordinary differential equations are easier to solve than partial differential equations. And if any one of you has ever tried to do this on a computer, I think you'll believe me, okay? So what this comes out to do is that if you have a radius and you have a time, if you have an isothermal problem, you have a sound speed. So instead of looking at the equations as a function of radius and or time, we construct a new variable, which is radius over time, and we put the sound speed in here to make it dimensionless. Okay? Then you have a dimensionless surface density, a dimensionless velocity, and a dimensionless magnetic field. And not only do we make the variables dimensionless, we make them functions of a dimensionless variable. And then all of the time dependence is scaled out front. So each one of these things we're solving for has a power law time dependence out front. And then you get reduced differential equations, which depend only on these dimensionless variables. So now we've reduced the problem considerably. Now I'm going to skip over the actual math of this and just jump to the solution. So I'm also going to introduce you to the idea that every time we have things that I'm sort of hedging about, the dragon will show up, okay? So I have to come clean and tell you a few things. In this problem, if you scale out all of the time dependence, you can't actually do the diffusion, so you have to do an iterative loop back and forth between them. And there's a strange interplay between the two-dimensional approximation we're making and the three-dimensional approximation we're making. Remember, we started with this fluffy disk, and we transformed it down to a thin disk in order to do the problem, and then we have to fluff it back up. So we're making an approximation in doing that, so we have to be careful about that. There's also a very subtle mathematical issue in how you treat the magnetic tension, which I'm not going to get into. But the bottom line is what I was saying earlier, that each one of these individual things we can deal with, and we know what we're doing always better than a factor of 2, but when all of these things kind of cancel out, so that the final solutions are kind of good at the 10% level. And here's why it works. When you go through all of this physics, what you get is just a different version of the diffusion equation. Now remember what we're doing here. We just have magnetic fields that are diffusing outward. Okay? For those of you who came in late, what we're doing is we're making molecular cloud cores, which are the things that are going to form stars. And the way in which they form is that magnetic fields are diffusing out of them. So if the magnetic fields are diffusing out of them, we have to write down a diffusion equation to describe that diffusion. And then the rest is mathematical detail. Okay? But here's the deal. In the dimensionless version of this diffusion problem, we have a dimensionless diffusion constant, not surprisingly. But the beauty of it is that it's a small number. Okay? And that lets us, because it's a small number, it lets us expand in terms of it. It means all of the velocities and stuff are going to be functions of a small parameter. So to 0th order, the velocities are 0, and to 2nd order, they depend on this thing linearly, and so on. So we can make various approximations. The first approximation is to assume that the gravity is spherical. And when you do that, you get simple forms for the solutions that we seek. Okay? So remember, what we're trying to do is we're trying to start with a core that has uniform density, and then we want to let the magnetic fields diffuse out, and we want to form a centrally condensed core where the density is peaked in the center and falls off. So the first version of the approximation that I described has this is the processed density profile. So it's the dimensionless version that I described. It's got a constant density center, and then it reaches a power law as you go outward. It started by being flat, but at any given time it will have this form. And then look at the velocity. In the center, the velocity has to be 0, because you can't go through the middle of a spherical thing. That's always the boundary condition at the middle of the star, or any spherical thing. But overall, the velocity approaches a value that's constant. And look at what constant value it is. It's a half. Well, what does that mean? Remember, we've non-dimensionalized everything in terms of the sound speed. So this tells you that the inward velocity on the outside of a core is half the sound speed. Now, why is that important? Well, if you remember back about 20 minutes, one of the things that we want to solve for is the fact that when you make a core, it's not quasi-static, but it's condensing, not collapsing. And the inward velocity corresponding to that condensing motion is half the sound speed. So this theory naturally gives you half the sound speed. Now, the reason why it naturally gives you half the sound speed is because of the particular size of that dimensionless diffusion constant that I showed you. But that is set by other physics, namely the magnetic field strength and the coupling constant, or the coupling terms that determine how tightly the magnetic field couples to the ions and how tightly the ions exert forces on the neutrals. But those are set. Those are just things that we measure in a lab. And with those values, we automatically get the condensation speed. Now, because this problem is self-similar, as you evolve the core, you get different versions of this structure. And finally, after you've gotten the full solutions, you can make analytic estimates or analytic fitting forms that fit the actual numerical solutions to 1 and 2%. Okay? So let me skip ahead to this. So this is what the time evolution of a core looks like. Okay? So remember, we're starting with a cloud. We want to see how these subcondensations form. And remember, the reason why we're doing this, just to remind you again, subcondensations are the sites of individual star formation events. So this is the first big step in the star formation process. We want to produce these initial conditions where these things will collapse and make a star. So what we're going to do is we're going to measure time before the collapse event. Remember, the cores start in the sea of molecular cloud of material. They get more and more centrally concentrated with time. And then at some moment, they will collapse. So they're condensing for a while, and then they collapse. And once they collapse quickly, and they form the star in the middle, okay? So the time of collapse is going to be 0, time 0. So the time before the collapse will be negative, and the time after the collapse will be positive. Got it? Negative before collapse, positive afterwards. So at time minus infinity, there is no core. Ain't nothing happened yet. I can pick up the story 1 billion years before the moment of collapse. And at that time, my density profile, which I've now switched back to physical units, is it's got a density of 10 to the 4 for a very, very long inner core, and then it has a short power law tail at large radius. Okay? This curve here, which is at about 1/3 of a parsec, is more or less the size of the core that we identify as a core when we look at it with a radio telescope. So this is where your observations are dealing with, okay? Now, I showed you this picture of a core earlier on, and I said it looked like a Bonner-Ebert sphere. And a Bonner-Ebert sphere is a sphere that has a tiny little power law outer bit and a large inner core of more or less constant density. So the cores that we see, the ones that we can map out well, generally have big central regions where they have more or less constant density. They're not highly peaked in power law. But there's a reason for that. You see that a million years before collapse, that's what the cores look like. If you look 100th of a million years before collapse, as time proceeds, the central regions become more and more centrally concentrated. So if you look at 100th of a million years before collapse, the constant density region has shrunk to this size, and you have a long power law version. But here's the deal. It turns out a 100th of a million years is less than a million years by about a factor of 100. And that's important. That means that you have to look at 100 cores to see what this centrally peaked. Almost all of them you see are more like this one, which are the ones that we see. So this time evolution, the point of this is that this time evolution is perfectly consistent with the data that we see. Okay? Remember, we began by saying we can understand this process, but we can also touch base with data at each point along the way. So we see molecular cloud cores that are mostly not centrally condensed. We see some that are centrally condensed, but we know why. So the time evolution of this predicted is that you have a lot of time spent in this sort of spread out realm and less time spent as the core gets more and more centrally concentrated. Okay? Now, if you were to follow this all the way to t equals 0, this density would become a pure power law. The number density would become a pure isothermal sphere, which is an unstable isothermal sphere, which has a density profile that goes like 1 over r squared. Now, you can never really reach that state because it's singular. You'll immediately realize that if the density goes like 1 over r squared, what happens at the middle? Well, you have an infinite density. So you're never really going to reach that. But you'll get pretty close. And either way, at time t equals 0, you have this, what we call the gravomagnetic catastrophe. It means that the magnetic field is no longer able to support the cloud at all, and it's going to move from this slow and steady condensation phase to a dynamic collapse phase. So we're going from slowly condensing to quickly collapsing. And the transition happens at t equals 0. So if then you look at t equals 0 and you ask what happened later, well, I'm going to show you the density profile for collapse solutions. Okay? Well, this is the density as a function of distance again in the same units. At time 0, you have a perfect isothermal sphere, which is a 1 over r squared power law, which is a power law that extends all the way in. When the collapse proceeds, the inner bits fall in first, so the region inside subradius has lost its material and becomes a different power law. And at a later time, even more stuff has fallen in. You have a much longer region of the shallower power law, which connects onto the steeper power law further out. So this region that marks the boundary between the inside that's collapsing and the outside that's still condensing is this point here, this point here, this point here, this point here, this point here at subsequent times. And that boundary marches outward in time. In fact, it marches outward at the sound speed. And that actually makes physical sense, because if the collapse proceeds from the inside to the outside doesn't actually know that the middle has collapsed yet. It takes a while for a signal to travel from A to B and say, hey, we're collapsing, because we're supported by pressure, and pressure travels at the sound speed. So it takes a while for the outer parts of the core to know that the inner parts have collapsed. So the communication of, hey, we've collapsed inside, propagates outward at the sound speed. All those equations I showed you show this, but the physics of it is actually quite easy to understand, even though the equations are, well, that's kind of our job, okay? The velocity does a similar thing. These are free fall velocities on the inside. So once the inner bits have collapsed, you have free fall velocities. And then the free fall velocity will decrease until it reaches an asymptotic value. This asymptotic value is about half the sound speed, which is the original condensation velocity that the cores exhibit. Okay? Now there's actually more we can get out of this. I'm not going to go through the math on this, but it turns out that in order for all of this to work, you get an eigenvalue out of this, and that defines a mass scale. And when you put in the numbers, the mass scale you get is a few times the mass of the sun. What does this mass scale mean? This is the mass scale that this diffusion process can produce. Loosely speaking, what it means is that inside this mass scale, there's a boundary. The ambipolar diffusion, the magnetic field diffusion process that I'm describing, operates, and this sound speed can propagate, well, and then that region can collapse and communicate the collapse outward at the sound speed. But you can't do this over the whole cloud. Once you get far enough out, the material belongs to the cloud itself and not to the core that we're talking about. So there's a well-defined mass scale that's determined by what the magnetic field can influence in the core. And that's what this M core value is. Okay? Now what's significant is that the mass scale is a few times the mass of the sun, 2 or 4 or 6. The mass of the stars that are forming are typically a half or a quarter, because most stars are actually M stars, right? They have a mass of 0.2, 0.3, 0.4 solar masses. So this mass scale is 10 times bigger than the mass of the stars that are forming. Not exactly a factor of 10, but in order of magnitude a factor of 10. We'll come back to that, okay? So to wrap up what I'm talking about here, and perhaps I've given you more detail than you want in how this actually works, but we have a perfectly good working analytic description of the magnetic field diffusion process. And what it does is it smoothly connects the diffusion process, which is the core formation stage, to the subsequent collapse phase. So the picture that you should have in mind is that you start with a more or less uniform cloud. It's supported entirely by magnetic fields. As the magnetic fields diffuse outward, the inner parts of that core become denser and denser and denser and denser and denser. If that process could proceed to completion, you would get a perfect power law, 1 over r squared density profile, a perfect singular isothermal sphere, just like in your astronomy textbook. Okay? And the diffusion process naturally produces that, with one exception. It's not static, it's not hydrostatic, but there's this extra velocity, this condensation velocity of half the sound speed. Then there's this transition from that condensing phase to a collapse phase where the inner parts of that core collapse, and then the next outer parts collapse on top of it, and then the next outer parts collapse on top of it. And you get this wave of collapse that propagates outward. So the core becomes denser and denser and denser and denser and denser. You reach this gravomagnetic catastrophe, just because we had to give it a cool name, and then it collapses, and then it sort of drains all the material on the inside into a star in the middle, okay? And this process has a number of observational successes. One is that we produce naturally the half a sound speed condensation velocities that are observed. This process takes about 1 million years, which is more or less commensurate with the timescale we derive by looking at molecular cloud core statistics. We get an eigenvalue which defines the inner and outer boundary of the core, the part that belongs to the core and not the cloud. That's a couple to several solar masses, which is what we measure when we measure ammonia core masses. And it also explains the observation that the cores have this long, nearly constant density inner region, because the cores spend most of their time at that state. There is a difference, though. People have modeled those Bonner-Ebert spheres with a static model, but then they measure the fact that the velocities are half the sound speed, right? So the model that they're actually using to fit it is inconsistent, whereas this one not only explains it, but is consistent with that same head start velocity. Now, I'm going to switch gears slightly on you here. So we have this picture of collapse. That's what you're supposed to take away so far into the story. But it turns out that the cores themselves are also moving. So if you look at a cluster, this is a small cluster, which one is this? No, this is 1333. You see that there are little condensations, which are the cores that I was talking about. Each one of these is collapsing, first condensing, and then will eventually collapse into a star, controlled by magnetic fields in the way that I just described. But we also see that before the cores have collapsed, they're moving with respect to each other at, again, half the sound speed. Now, once the stars form, this region has both cores which have not made stars yet and actual cores that have made stars, so they have stars. The stars are moving ballistically. They don't feel anything but the gravitational potential, and they're moving at a typical velocity of a kilometer per second. Okay? The sound speed is 0.2 kilometers per second, and half the sound speed is 0.1 kilometers per second. So you have the case where the stars are moving ballistically, and the core-to-core speed is 1/10 of a kilometer per second, which is 10 times smaller. Okay? So there's 2 points I want to have you come away with this. One is that if you're moving at 0.1 kilometers per second at half the sound speed, and you do so for the time it takes to collapse, which is 1/10 of a million years, that's the time that this collapse phase lasts, you'll only move 0.02 parsecs. This whole thing here is 0.2 parsecs, so 0.02 parsecs is that big. In fact, that's what this little red circle is. That's 0.02 parsecs. So what this means is that while the cores are forming, collapsing, during the time it takes for them to turn themselves into the stars, they're not moving. They are observed to be moving, but they don't move so much that they ever run into each other. So you've seen, or some of you have seen, these numerical simulations of star formation that are completely dynamic, where you have like these cores running into each other and all these collisions and stuff. The reason why they get that is that they crank up the density to be 1,000 times what the actual observations show. Because if you actually use the numbers, what you find is that during the time it takes for a star to form, this is the distance you move. After you form a star, you have much more time, and then you're whizzing through this cluster over and over again. And that's what I'm going to talk about in the third lecture. Okay? But the initial conditions say I don't have to talk about it in the initial phases. Okay, the second thing is that they are not static. They are, in fact, moving, and they're moving at this speed, which is 10 times less than the virial speed, but nonetheless they are moving. Can we understand that? Well, here's the cool thing. We have a friction exerted on the volume of the core by the magnetic field due to the fact that they're being pulled on by the gravitational potential of the core. This is the same physics that we just went through to describe the formation of the core. Remember, to describe the formation of the core, we had to specify the friction exerted on the neutral component by the ions, because the ions are tied to the field, and we had to specify the field strength. And I argued that that picture of core formation had many observational successes. We could understand what we see in terms of core properties. Well, those same magnetic field properties and those same frictional terms exerted on one species by the other will also allow the magnetic field to exert a frictional force on the whole core due to the same physics. So we have this picture where the cores are being pulled in by gravity, and they're being held up by the magnetic field friction. And they will reach a terminal velocity, and the terminal velocity that they reach is given by this formula, which when you plug in the numbers happens to be 0.1 kilometers per second, which is the same speed that we see them moving at. So the balance of the frictional drag exerted on the core by the magnetic fields through the friction between the ions and the neutrals, the same physics that led us to core formation, also gives us the same speed that we see the cores moving through their clusters. It's just a consistency check on this picture. Now, we have a problem. Marty Dragon has showed up again. And the problem is that we don't have a uniqueness theorem. So I've described core formation in terms of magnetic field diffusion. And it works. And we can, through honest calculation and honest theoretical prediction, or post-diction at least, account for many of the observational properties we see of cores, their condensation velocities, their motions, and so on. However, it's possible there could be another completely different theory that also works. We don't have a uniqueness theorem. In fact, the people who do MHD numerical simulations put magnetic fields and gravity in a big box in their computer, and they run it, and they get things that look like cores. And they argue that what I just told you is not the story, but rather the story is there's a story of turbulent fragmentation. Now, I think that if you take those simulations at their most extreme value, in order to get dynamics that depart from what I described, they have to jack up the densities to be 100 or 1,000 times denser than what the actual interstellar medium does. But that doesn't mean that they're wrong. Turbulence is, in fact, almost equally important in the interstellar medium as the magnetic fields. So what we really need to do now is we need to revisit this magnetic diffusion problem in the presence of turbulent fluctuations. And we'll see what that does to our problem. And again, I'm going to show you equations, but I'm not going to solve them. There's something to point to. This is a version of the magnetic field diffusion equation I showed you earlier. Remember, we had d by dt of b over rho, and d by this of a diffusion constant, d by this of the magnetic field. And the diffusion constant depends on b squared and all these things that we saw before. But what I'm going to do now is I'm going to let both the field, the magnetic field, and the density field itself fluctuate due to turbulence. So I'm basically adding turbulence into this problem by hand. I'm saying that I have the field, but I'm going to let it wiggle. And the way I'm going to let it wiggle is I'll multiply b by 1 plus c. That's just my way in which I'm introducing it. So if c were 0, I would get no new effects. But this you can think of as a random variable, which allows you to introduce fluctuations. And if I let the density also have a random variable, I get this random variable showing up in my equations. Then I have to decide how to choose the random variables. Okay? Now, we'll do that by looking at observations. What you see, well, what we can do is we can choose the amplitude of these variables, these fluctuations. If they're 0, you get no effect. If they're huge, you get a huge effect. We also have to specify their sampling time. In other words, how often do you choose a new value of it while you're doing the calculation? Now, in this problem, we're talking about a magnetically supported core. So in a regular core, we just argued that pressure waves travel at the sound speed. So here, the information that you have a new magnetic field value has to propagate at the Alfvén speed. So you can only have a new value of the magnetic field every Alfvén crossing time. So I will introduce new values of these random variables every Alfvén crossing time into the problem. But I still get to set the amplitude. But the amplitude basically determines how much extra non-thermal line width you have in your observations. Remember, these are molecular clouds, so we have molecular lines that tell us where the clouds are and what their properties are. The molecular lines have both a thermal component and a non-thermal component. And the non-thermal component is usually ascribed to turbulence. So the amplitude of that non-thermal component tells me the amplitude of the turbulence. So now what I can do is I can do this diffusion problem in the presence of these fluctuations and see how long it takes. So here, I'm plotting the time it takes in dimensionless units as a function of the amplitude of the turbulent fluctuations. So in the absence of any fluctuations, it takes 12.5 units of time, it turns out. These are actually Frank Shu's dimensionless units from 1983, so 12 doesn't mean anything. But when you put in numbers, it's a few million years, okay? As I add up more and more turbulence, each time I do the simulation, I get one of these dots. So you see that there's a general trend that as I increase the amplitude, the time it takes to diffuse the magnetic fields out goes down. But you also see another effect. Namely, each time I do the problem, I don't get the same diffusion time. Each time I do the problem, I get a different number. Of course, that's just the hallmark of chaos. That's the hallmark of sensitive dependence on initial conditions. That's what you get when you introduce stochasticity into a problem. But this is what the real cores are doing, okay? So you can summarize this way. If I have core formation, in other words, the magnetic field diffusion problem we've been doing, and I do it with no fluctuations, I get one number, and that number is here. If I add fluctuations, two things happen. One, because the fluctuations make the fields diffuse faster, the peak of the distribution goes from here to here. So I increase the speed, I decrease the time it takes. But I also move from having only a single value to having a distribution of values. So each time a core forms under effectively equivalent initial conditions, it will form with a different speed. The ambient polar diffusion time will have a distribution of values, and that's something we also have to take into account. So the introduction of magnetic field, the introduction of turbulent fluctuations into the magnetic field changes our diffusion picture of cores by speeding up the diffusion rate and replacing the formation time with a distribution of values. But it also retains all of the successes that I described earlier, okay? Now, I already described in words what happens after the core is formed, how it collapses from inside out. In the interest of, since I talked a little bit too long on other things, I'm going to skip over the actual physics of the collapse picture, and we're going to have to rely on the qualitative description that I gave earlier, because I want to get to the last little bit. So again, we have this great big, this general picture where cores form out of the cloud. They form by field diffusion. They get denser and denser and denser and denser. They collapse from inside out. The collapse flow forms a star at the middle and stuff drains onto it. Okay, that's our picture. Now, what we want to know, and again, what the cosmologists want to know is, well, what's the mass of the thing you're forming here? Now, what we find is that there's lots of mass scales. But this inside-out collapse picture that I described doesn't have a single well-defined mass associated with it. Instead, it has a well-defined mass infall rate. In other words, if you have a power law distribution of density, which is what the magnetic field diffusion picture produces, and you let it collapse, it will collapse at a well-defined rate. But there's no mass scale. So what's the mass of the stars that you form? Well, first of all, what is that rate? Well, the rate is given by some dimensionless factor of order unity times a cubed over g, where a is the sound speed. When you plug in sound speeds that we see in clouds, this value becomes 10 to the minus 6, 10 to the minus 5 solar masses per year. which means that it takes about 1/10 to 500,000 years to form a star. So we have a well-defined rate at which stars are made. In fact, all stars are formed in a couple tenths of a million years, it turns out. Because we think that the higher mass infall rates produce the bigger stars. So even though a bigger star has further to go to gather its mass, its infall rate is bigger, those things nearly cancel. So within a factor of 2, all stars form in a couple tenths of a million years. Now, that's a short amount of time compared to the disk lifetime. It's a short amount of time compared to the planet formation time. It's a short amount of time compared to the pre-main sequence lifetime, all of which are 10 million years. And it's a very short amount of time compared to the hydrogen burning lifetime, which is, for the sun, 12 billion years, right? The sun's only 4.6 billion years old now, but it will burn for a total of 12 or 13 before it's done, right? Now, there are mass scales formed by the core, in that I said if you have a power law, there's no mass scale, but we don't have a pure power law. Because if you have a density profile that's a power law, you have an infinite density at the middle, and that can't happen. And on the outside, the power law cannot continue forever either. First of all, that would require an infinite amount of mass, which would be sort of a problem. But also just practically, as you go out far enough, you have to join on to the background of the cloud. So there are, in fact, mass scales that the core has. There's an outer boundary. This is the boundary at which the core joins on to the outer cloud. And in the particular version of the problem that I described briefly, that's actually set by an eigenvalue and has a value of several times the mass of the sun. On this slide, I called it 6. Okay, so there is an outer boundary to the core. Outside, the power law distribution joins smoothly onto whatever the background core is doing, or background cloud is doing, excuse me. On the inside, the power law, 1 over r squared density profile doesn't increase without bound to infinity, but it will turn over to some constant density in the inside. There's a little mass scale set by the extent of this constant density core of the core, you might call it. And that's set by the maximum density that can be obtained. Now, we see densities of millions in the cores. The average density is much smaller, it's more like 10 to the 4. But the peak densities we see are somewhere in this neighborhood. So the mass scale that's enclosed in this constant density realm in the middle is about 1/100th of a sun or so. But here's the deal. The inner boundary of the power law region sets a mass scale which is much smaller than a star. The outer boundary of the core sets a mass scale which is much bigger than a star. Now you might say, well, 6 solar masses doesn't sound so bad. We could have a star that's 6 solar masses. But this is for a core that's going to make a half a solar mass star. So it's 12 times too big. And here's my point. 12 is infinity. And what I mean by that is the following. If the core is forming from inside out, where the outer or the inner parts are falling in and the next outer bits, once you get 1/10 of the way in, or 1/12 of the way into that process, you have enough mass to form the final mass of the star. It doesn't matter whether there's twice more mass than you need, or 4 times more mass than you need, or 10 times more mass than you need. You're done anyway, right? It's like when you're at the Thanksgiving table and you're eating, after you've eaten your 3rd turkey, it doesn't matter that there's 12 more. You're still done, right? So, this mass scale 1 is 10 times bigger than the masses of the stars that you're forming, but it might as well be infinity. Some other process has to say, once I've got 1/10 of this mass, I'm done, right? So the cores, even though they do have mass scales associated with them, do not set, at least not by themselves, do not set the mass of the stars that they form. Okay. Now, according to my clock, I only have about 10 minutes left, so I'm going to speed up just a little bit so that I don't inundate you too much. So, what we've talked about is we've talked about the fact that we have collapse solutions that piggyback nicely onto the core formation solutions that we described. We can include with these what I call head start velocities. These are these non-zero starting velocities, the ones that we see. We can also incorporate overdense initial conditions and lots of other generalizations. But the basic picture that you get out of all these collapse solutions is something like a core that looks like this, and then they all collapse with a well-defined rate. The rate is set by some factor m naught over a times a cubed over g, where a is the sound speed. This value m naught, this dimensionless value up front, depends on the condensation velocity. If the condensation velocity is 0, so you're starting in a completely hydrostatic state, this value is very close to 1. It actually turns out to be 0.975, which is 1. If you use the observed half a sound speed value for the starting velocity, the velocity you get from core formation, this value increases to about 2. And that's probably the single value you should use, right? Oh, so I think I should do this plot of, oh, I know what my point was. So we talked about this, we showed you this already, that cores have constant density centers. So, and I also showed you or argued to you that the cores have a well-defined mass infall rate. The mass infall rate is going to be constant only while the power law part of this distribution is falling. With the centrally, if you started with a big central core like this and you let it fall, you would get a big spike in the infall rate. So if I plot the infall rate versus time, if I have a hydrostatic Bonner-Ebert sphere with a big density or big region of constant density in the middle, I get nothing for a while. If I plot the m dot versus time, nothing falls to the center for a while, and then I get a big spike, and then it slowly asymptotes to a constant value. If I do the same kind of core with a starting velocity, which is what we see, you get a much smaller spike, and you reach the asymptotic constant value much quicker. So the action of the starting velocities actually has the effect of making the mass infall rate even more constant. Just one effect I want to mention very briefly is that we've seen how core formation is controlled, at least in part, by magnetic fields. And we showed that the magnetic fields, along with turbulent fluctuations, give you a distribution of answers. So each time you do the problem, you get a different answer. Each time a core forms, it will form at a different time. There's yet another complication, namely the ionization rate can vary from place to place, and the ionization rate sets the coupling between the ions and the neutrals of the magnetic field, as we've seen. So just think about it this way. Where do cosmic rays come from? Well, ionization is produced by cosmic rays. That's the thing you need to know. But where do cosmic rays come from? Supernovae, right? Well, where do supernovae come from? Well, they come from the death of massive stars, but massive stars are formed in molecular clouds. So supernovae, when they go off, are generally not so far from their birth clouds because they live, die, and blow up in 10 million years. So what most people do is they just use the galactic average cosmic ray rate. But if a supernova goes off inside a cloud, it's going to lace the cloud with cosmic rays, and they will be controlled by the magnetic fields in that cloud. It will take them a while to diffuse outward. So if you turn all the knobs to one side, you can get an enhancement of 1,000 in the cosmic ray flux for about 1 million years. On the other hand, if you actually do the magnetic mirroring problem, it's like a Jackson problem for those of you who had to take that course. Cosmic rays spiral in on magnetic fields and they spiral out as they reach denser regions. If you add turbulence to that, that can actually make it even more effective. So you have all these different knobs to turn where the cosmic ray ionization rate could be 1,000 times bigger or 1,000 times smaller than the single value that everybody uses. So that's just a warning to you. And what that means is that all of these processes that depend on magnetic fields and magnetic field coupling will vary from place to place and time to time and instance to instance. So there's not one answer to the problem, there's a whole distribution of answers, right? Now the last thing I want to talk about, well, I still have a few minutes left, is how to put rotation into this collapse. So, and I'm just going to do this briefly, but I'm going to show you that we have the equations to do this, okay? So the picture we have is that we make the core, it reaches the centrally condensed state, it collapses from inside out. And so far I've talked it as if it's a spherical collapse, okay? Well, there's a little bit of angular momentum left. So on the outside of this collapse flow, it is in fact spherical, or spherical to a good approximation, and you can believe everything I said. But inside, the angular momentum starts to matter. So the way in which we address that is you imagine that the thing that's becoming a star is at the origin. Once the parcels of gas have fallen sufficiently far inward, they're influenced primarily by the gravitational potential well of the thing at the center. Okay? Now, if you're influenced by a single point body, the trajectory you follow is basically a Keplerian orbit. But since this is a Keplerian orbit with zero total energy because you're coming in from infinity, essentially, it's a parabolic orbit, not an elliptical orbit. But you also know from your Keplerian orbits that if the star is spherically symmetric, the orbit will be in a plane. But here's the complication. Not all things coming in will be in the same plane. So each parcel, which starts at a given starting position, will spiral in on a parabolic orbit in a given plane. But then what you have to do is you have to add up all those different planes to give you the density distribution of the composite distribution. And that's what these equations here do for you. You write down zero energy orbits, you write down an orbit equation for each plane, and then you transfer each plane into regular spherical coordinates. And you get a bit of a mess mathematically, but you could write down the non-spherical density distribution for that case. And the reason why this is important is, one, it works, but two, it tells you the disk properties. And it also raises an important question. We get yet another mass scale out of this deal. Given that we have a certain amount of angular momentum in the core to start with, most trajectories will actually not fall far enough inward to hit the star, but instead they will hit a disk that collects around it. But some fraction of the material that comes in does have low angular momentum, because the stuff along the poles will come in, and will hit the star. So what is that number? Well, it's this number, in terms of the sound speed, the stellar radius, g, and so on. But what is that number? It's about 5% of the sun. So what this tells us right away is that most of the material that becomes part of the star does not actually land on the star. Instead, it lands on the disk that collects around the star. And then the disk will have to somehow transfer its material from the disk onto the central star. So disk physics is important, and we're going to talk about that tomorrow. Now, it turns out that rotation sets another scale. If you have even a small amount of angular, or a small amount of rotation, of course going like this, if you go far enough outward, the specific angular momentum increases to the point where that stuff can never fall in, okay? So the rotation also sets an outer boundary to the core. That's given by this formula, which turns out to be, in this particular number, 5.7 solar masses times the sound speed cubed, and the rotation rate in these units, which we see the -1. The outer boundary set by rotation is actually kind of sort of the same as the outer boundary set by the magnetic fields that we saw earlier. So there's actually two reasons. There's two effects that separate the core material out from the background cloud. There's a magnetic field sphere of influence, and there's sort of a rotational sphere of influence. And coincidentally, they're about the same, and they're both about 10 times the mass of the star that forms. Okay? So I can skip that, and skip that. For high mass stars, we have to include the effects of radiation pressure. And you can actually do this in a nice, elegant way, because when the trajectories of the infalling stuff is far away from the star, the radiation pressure is weak and you don't have to worry about it. But when it's close to the star, where you do have to worry about it, you can include the radiation pressure by adding an extra force. So you can do the same problem that I just described schematically a couple slides ago, where we have incoming trajectories, but instead of moving in a Keplerian potential, you're moving in a Keplerian potential plus an extra term due to the force exerted on the bodies by the radiation pressure. So you just have modified orbits. And that gives you a modified infall collapse solution. And the trajectories look sort of like this. When you're coming in from afar, you don't care. But once you get close enough, the radiation pressure turns around the incoming parcels. And this effect starts to play a role once stars get to be about 7 times the mass of the sun. And what it does is that for high mass stars, this effect that material has to fall onto the disk is even more important. Because if this infall were spherical, the trajectories would have to come right into the star where they're seeing the brunt of the radiation pressure, and then they would get completely repelled away. However, if you're forming a star with a disk around it and you have rotating trajectories, the material can fall to larger radii and hit the disk before it gets close enough to the star for the star to blow it away. So whereas you think this rotation in the disk problem actually inhibits star formation, and in a way it does, because stuff has to hit the disk and somehow get onto the star. For high mass star formation, it's the only way you can make a high mass star. In the presence of radiation pressure with ordinary solar metallicity, you could never make a star bigger than 7 solar masses if you had to do it spherically, because at that point the luminosity of the star would blow away everything and separate itself out at 7 solar masses, and you'd never make a 20 solar mass star. The only way you can make a big star, where big means bigger than 7, is by having the material hit the disk first. So whereas the rotational effect is an inhibitor of star formation for low mass stars, is an enabler of star formation for high mass stars. And that gives us an ordering of scales that we have to keep in mind. There's a stellar radius, which is set by the hydrostatic structure of the stellar-like thing in the middle, and this is roughly solar size. For a forming solar mass star, while it's in this early phase, it has a radius of about 3 solar radii, but order of magnitude is still the size of a star. There's the size of a disk, which is about solar system size, 10 to 100 AU. There's the radius of the expansion wave, which is the collapsing region, which is about 1/10 of a parsec. And then there's the radius of the core, which is about 10 times bigger. This radius here is the stuff that's collapsing that will form the star, that will get to this size scale, some fraction of which will get to this size scale. The core itself is 10 times bigger than this, and the core belongs into a clump, which is the larger scale structure, which will form a cluster, and then that belongs to the cloud, which is the whole million solar mass complex that we have. But we have actually an interesting and useful separation of these size scales, and there's a corresponding separation of mass scales. Now, after all of this, when you read a textbook on star formation that's actually not on star formation, they say, well, it's all the Jeans mass. Which leads to the question, what the heck does the Jeans mass have to do with anything that I talked about? Now, Sir James Jeans was not wrong, okay? But that does not mean that it describes everything. So what is the Jeans mass? Well, you write down a constant density cloud you make it infinite in spatial extent, you consider an infinitesimal perturbation on it, and then you look at the geometry of plane waves acting on that constant density background, and you get this famous dispersion relation, which I'm guessing most of you did as a homework problem in some astronomy course. I realize there's some biologists here who might not have done this, but if you had been, you would have done this. And you can solve this for k as a wave number, 1 over a wave number is a wavelength. You can solve that for the wavelength and get a Jeans wavelength. You can turn that into a mass scale by taking the wavelength cubed times the density. And lo and behold, you get the Jeans mass. Now see what the Jeans mass depends on. It depends on the sound speed, on g, and the density. Okay? Now clouds are kind of sort of isothermal. So assigning a temperature to a cloud is actually a very sensible exercise. But here's the problem. The Jeans mass depends on the density. And the density in a molecular cloud varies by a factor of at least 1 million, maybe 100 million. So if you decide, so what people generally do is they pick the density of that range that gives you a mass of 1 solar mass, and then they say it works. What I would urge you to be cautious about is that you actually get 1 million different Jeans masses. So if you pick the one that you want, you will get the number that you want. I agree with that. But I would say that this whole theory is a little bit too incomplete, because you can get any number you want just by picking the density you want. Moreover, if you pick the average density of the cloud, the Jeans mass you get when you plug in that number is like 1,000 solar masses, which is actually not the mass of the average core. So we have this whole summary of mass scales that I will put on. All this stuff will be on the web eventually. So we have the Jeans mass. We have the mass of the material that goes from the rotating core directly onto the star. We have the eigenvalue of the core scale set by ambigular diffusion. We have the magnetic critical mass. We have the rotational critical mass. And it turns out that this mass scale and this mass scale set the core scale. This mass scale is much larger. This mass scale is much smaller. And this mass scale is anything you want it to be. Now, I'm going to close by going back to the magnetic flux problem and the angular momentum problem, and then we'll have, there better be coffee, right? Okay. So, remember the two big problems that are sort of the classic problems in forming a star is that the clouds have too much angular momentum and too much magnetic flux. So, how do you get rid of that? Well, it turns out that we saw that the magnetic flux scale is 1,000 solar masses, okay? So I think what happens is that on a scale of 1,000 solar masses, you form what I called earlier a clump. These are the size scales that will become clusters or protoclusters or embedded clusters. Not all of these will live to be the open clusters that we learn about in astronomy, but they'll be cluster-like things, okay? And I'll talk about those more in my third lecture, at least a little bit. So on the largest scale, the magnetic field is not strong enough to support things bigger or than 1,000 solar masses, so you'll form clusters on that size scale. But to form an individual star, you have to get rid of the magnetic field, and that's what this magnetic diffusion process, which I talked about at some length, does. As you saw from the equations, there's more I could have talked about, but that's what it does. So the magnetic field is lost in two stages. In one stage, it collapses to clumps, and then the other stage, ambipolar diffusion gets rid of enough for the core to collapse. Along the way, the magnetic fields also set a boundary between the region that belongs to the core and the region that belongs to the clump or cluster, which is the larger scale thing. Now, what about angular momentum? Well, angular momentum is also lost in stages. So the cores have a much smaller specific angular momentum than clouds. And the reason for that is that the magnetic field sets this boundary between the core and the cloud. And that same process breaks or reduces the rotation rate of the core. So the rotation rate of the core is smaller than the rotation of the cloud because of magnetic field breaking. And that actually gives you the right answer. But then in order for that core to collapse to solar system size scales, it has to lose flux. And the way it loses flux is through a diffusion process. So the flux diffuses out. And that leaves us with a almost field-free structure that's rotating. But it's still rotating much faster than a star can, or with too much angular momentum to be contained in a star. So that structure will collapse not to stellar size scales, but to solar system size scales. Now remember, the sun is 10 to the 11 centimeters, 7 times 10 to the 10 centimeters. The solar system is 30 AU, which is almost 10 to the 15 centimeters. So there's a 10 to the 4 size scale between stellar sizes and solar system sizes. So then disk physics, which operates on the solar system size scale, transfers most of the angular momentum from the disk or into the disk and allows most of the material to go onto the star. Okay? Now before I conclude, let me just give you one piece of physics which I'll come back to tomorrow. Why does this make sense? In other words, we have angular momentum. It makes sense that the cores would be braked by magnetic fields. Then they collapse to solar system size scales. That's just conservation of angular momentum. But why is it that once you have a disk system, you put most of the material onto the star and still have a disk? Why does that work? Well, there's a simple way to understand that. And that's what I want to leave you with. What does any physical system do? It moves to a lower energy state, right? So if I have a star disk system, what's the lowest energy state it could possibly have that still preserves or conserves angular momentum? Well, I get a lower energy state by moving it down the gravitational potential well. So the lowest energy state is to put everything in the star, because that's the lowest you can go. But I have to preserve angular momentum. So the best you can do is to put everything into the star with one proton at some really large radius like infinity that has all the angular momentum. Now let's look at the solar system. This is exactly what we got. All the masses of the sun, all the angular momentum is at one proton at infinity, which we call Jupiter. Seriously, all the angular momentum is in Jupiter and Saturn. They have a mass 1,000 times less than the sun. Lowest energy state. That's it. How you get there is complicated, and I will introduce you to some of that complication tomorrow when I talk about disk physics. But the basic idea is exactly what you would expect, right? Once you have a solar system-sized star disk system, you're going to go to a lower energy state where you preserve angular momentum. That means you're going to dump most of the stuff on the star. You're going to retain some stuff at large radius to carry the angular momentum. There you go. So to conclude, what we talked about today, I'm going to list here, and this will be up. But what you should take away from this is, again, what I said before, we have this picture where clouds form. They're big. Cores form within them. They're much smaller than clouds, but bigger than stars. They form and produce their structure by having fields diffuse outward. Once they get too centrally concentrated, they collapse from inside out and form stars. The collapse is rotational, as in it has angular momentum, so you naturally form a solar system-sized object. And then somehow that disk will transform itself, that star disk system will transform itself into a solar system, and that's what we're going to talk about tomorrow. So I think you guys have tried your patience enough. Let me shut down here.